There's some in the rack over there.
I got a page and a half left.
Oh, good.
Think that's enough for today's notes?
Yep. Probably tomorrow's too. Depends how big you're ready.
Yeah, I missed that.
9 plus.
Yeah, I still get 31.
Yeah, no idea then. Could be that the cosine number was wrong. It could be lots of things.
Which is weird. You had the same equation.
Okay, so we are going to talk about
You showed us the video.
I know, but you don't have to keep talking. So we know how to find component form of a vector. Okay, delta x, delta y. So what we're going to talk about today is how do you do math with vectors. It's actually pretty easy. And then we're also going to talk about how do you show that graphically, because you can actually, this is where when I took physics, I was like, what the even heck are you doing? Because my teacher didn't teach it well, and I was like, I don't know. They're related. Okay, so there are two basic vector operations. Okay, so nicely enough, we do not multiply two vectors together. Recycling. Nothing. That's what I'm saying. Recycling, reusing.
Reduce, reuse, recycle.
Correct. Okay. So,
basic. You just introduced a whole new word.
Yep.
What do you mean basic?
Okay, two basic vector operations. Scalar is just a word. It's super low stress. There is subtraction, but we actually never subtract. Okay, so I'm going to put subtraction up here, and so your book would say there's only two. We will be doing subtraction. You just got to know how to do it. So the first thing that we're going to talk about is scalar multiplication. So when you're dealing with vectors, a number, vectors, a number that you're multiplying by is referred to as a scalar. Okay, so it's just a term. Because it's called a scalar because it changes the scale of the vector. Okay, it's going to change the size of the vector. Let me show you how that works. So let's say this is really easy. I know that the word scalar is weird. You're like, wait a second, this is supposed to be easy. This is easy. Okay, so let's say we have the vector. I want to make them decent size here so that we can see what we're doing, but not terrible. So if this is our vector in component form, right? Component form, that's what we call that. Okay. What are his components, first of all? What would his vector be written like this?
2, 1.
2, 1, right? So that's his x. So this vector is 2, 1. His x is 2 and his y is 1. So that coordinate point would be 2, 1. Starts in standard position with his initial point in the origin or at the origin. So if we were going to multiply, we'll just go this, to multiply. So let's say we're going to multiply by 2. So we're going to go 2 times 2, 1. Okay? You literally multiply the x and you multiply the y. number of a scalar. These are really sloppy notes today. So if you're going to multiply, you multiply x and y by the scalar quantity. Okay, so the multiple of this guy would be 4, 2. So watch what happens. Okay, so what happens if I multiply him? Here's his scalar multiple. So all it does is double the length. So the reason it's called a scalar is because it scales it up, keeps its same slope, keeps its same direction. It just changes its size. Okay, so that's all. You can. I don't really want to put this on the same one. Let's say I multiplied by 1/2 was my scalar. Okay, if I multiplied by 1/2, what would it be? 1 and 0.5. So he would be on the same line as this. So it would be 1 and 0.5. It would be there. Okay, so there would be a teeny tiny vector there. Well, I can multiply by a negative. So let's say I have multiplied by -2. So if I multiply by -2, yeah. So you multiply by a -2, we get what? -4 comma -2. That changes its direction. Okay, so a negative on the vector does change its direction. Okay, but otherwise, it's the same, right? The same slope. The slope of this will never change. It only will change the size of it. So it's a scalar quantity for that reason. So it's super easy to multiply by a scalar. So scary word, not difficult. Okay, so I'm going to show you, we're going to talk about, I don't have to talk about multiplying anymore. So let's talk about adding and subtract. Okay, this is where I got lost in physics class because vectors are physics related. So we're going to talk about how do you do this by the numbers, like how do you do this with two vectors, and then how do you also do it geometrically. Okay, so I'm going to give you grid paper because it's easier to do this on an actual grid paper so you can see it.
Grid. It even is named. Yeah.
Actually, what's the name order?
What's this paper about? Paper? It's from big ideas of that.
Yes, it is.
It's not my version.
Did I actually work it out? Wow.
Okay, so when we add or subtract, I'm going to write this down. It's a little bit confusing, so I'm going to write it down, and then I'm going to show you what it means. So let's say that vector u is 2, 7, and vector v is -1, 3. Okay, we're going to add these guys together. We're going to add them graphically. Okay, so to add graphically, the terminal point. So remember, terminal point means what? End. Terminal point is where it ends. The terminal point of the first one becomes the initial point of the second one. So you're going to graph them head to tail. Which this, well, I don't remember, know why. I don't know why it confused me when I was 15, but it did. Okay, so this, my people, is why we keep things in component form. Because if it's in component form, it's really easy. Okay, so I'm going to start down. I gotta give yourself a decent amount of room here. Okay. So what I want you to do is, first of all, graph vector u for me. Okay, vector u is 2, 7. If you need a ruler, you can get one out of the window. Okay, now, important thing about vectors is that it's not a line and doesn't continue, right? It ends at 2, 7. So there's your first vector, 2, 7. Okay, now, this is vector u, and we are going to stick vector v. We're going to graph vector v, but we're going to put, instead of starting at the origin, we're starting him at the terminal point of this guy. And this is why this is super nice. This tells us our change in x. So what is our x going to do? Left though, right? Because it's x, right? This is x. So it's going to go left 1. So we're going to go left 1. And this is our y. What's it going to do? It's going to go up 3. Okay, so instead of, let me show you this. If I had graphed v down at the origin, I would have the point -1, 3, right? This would be my vector down here. So instead of putting him at the origin, I'm starting him here instead. Like this becomes the quote unquote new origin. Left 1, up 3. Okay, so let me draw that guy in. This is vector v. Okay, do you guys get what I'm saying so far as how we show it? Okay, now the final answer, I got to make sure I'm pretty sure I know what this is called. It's called a resultant vector because it's the result, but I don't see that in my book. So maybe better not write that. Okay, the result or the final product, the final sum of your vectors is this. Okay, so this purple guy is u plus v. So all we're doing is illustrating. All we're doing, that's u plus v. So we see there's u, there's v, there's u plus v. That's an illustration. The answer to u plus v, like if I wanted to just add u plus v, I would literally add the x's, add the y's. Nope, because you got to know how to draw it too. Okay, so u plus v, if I add the x's, what do I get? I get 1. If I add the y's, what do I get? 10. Notice, whoops, angle bracket. Notice that is the point 1, 10. So we just illustrated, that's a 10, doesn't look like it. We've just illustrated what it looks like to add two vectors. So here is a real life example of adding vectors. Okay, so let's say that that vector u, the green one, represents the path that an airplane is traveling. Okay, but vector v represents wind speed and direction. Okay, if you're traveling this direction u in your airplane, but there's a wind current coming this way, that purple one is the actual path you will take, because the wind's going to blow you off your course. Okay, that's the real life application of vectors. There's a whole bunch of other stuff to physics, but I told you I'm not a fan of physics so much. Same thing's true in boating. Like if you're going against the current and the current's coming at you sideways, you have to course correct to get to the place that you want to go, because you have to counteract the current. I don't know. Well, there's not really a vector coming at you from the side, right?
You like go in one direction, but you got spin.
Spin is different than vector. Vector is acting in a straight line.
Wouldn't that be like a gyroscopical thing?
Don't know. Okay, so I would like you.
It's like when they hand them like the spinny things and they send them really trains.
We'll try to make this not quite so big. So I want you to graph u equals 3, 4. Okay. So I guess here's what I want to say. I want you to graph u plus v. Okay, so here's u, here's v. I want you to show what it would look like if you did it graphically. And then confirm that it looks the way it's supposed to.
Shoot, okay. I got you. I heard. I'm grabbing you.
Graph u. Go ahead and go. Javon told me I forgot to read that.
What?
Javon, she never said you did anything.
Actually, she did say it, doesn't she said
Actually, she didn't.
She literally said Javon. Told me. I said,
Yeah.
shut up, I did do it.
No, you didn't do anything.
Bring back Mr. Carter days. So that's it's a done. It's a dollar.
I got this. My graph looks amazing.
That was pre-Javon days.
Yeah, but it was in that.
Yeah, I know.
And then they was last year. No one addition.
He never
Oh, poo. I ran off my page.
Yeah. Yeah.
Why'd you do it this
I don't know.
I always look up the market, like 5 or 6 every day.
Routine.
Okay.
Right, used to it.
Yep, it does look like 1, 9. So u plus v is 1, 9. Now, every time you graph them, you're not going to have to, every time you add them, I'm not going to make you graph. Okay? Now, let's just real quick talk about subtracting. Subtracting is a little bit different. There's no actual subtraction of vectors. In subtracting, you add the opposite Okay, now it seems dumb to say, because if I'm just doing this numerically, it doesn't make a difference. But if I'm showing the graph, it matters. Okay, so let's say, so I guess let me write it out. So U minus V with vectors, like that's vector U minus vector V, I should have just put in bold, is actually equal to vector U plus -1 times vector V. Okay, so that's scalar. That's that scalar multiplication in there. So let me show you that one on here. And then that'll be it. So let's say we're going to do vector 4, 6 minus, this is U, and we're going to minus 2, 4, vector V. Okay, so when you graph these, it's so different. We'll see if I can. Okay.
Yeah. Just not the something questions.
Okay, so 4, 6. So we still kind of do it the same way, where we put the initial side of the V there, but you have to remember that when you're graphing this, it's the opposite of this vector. So it's going to be right to up to. Oh my gosh, you guys, I didn't even have coffee today. I can't even speak. Not 2 change in X, 4 change in Y, but opposite of that. So down to left 2, left 2, down 4. So this is going to be plus the vector -2, -4. There you go. That's what I'm trying to say. Didn't say it very well. So I'm going to go left 2 and down 4. 1, 2, 3, 4. So my other vector is actually here. Yeah, it's a very, very small triangle. Okay, so this is U. This is the opposite of V. So when you put it on your paper, it's not V. It's the opposite of V. Okay, so I want you to think about that a second, because V would be 2, 4. V normal would be positive like this. Okay, the opposite of V is -2, -4, which would be down here. That's what we tacked onto this guy, is the opposite of V. So down to, oh my gosh, I just need to stop speaking. So there is our final answer, which is 2, 2. So it does not change how we actually do the math. As long as you remember that you are adding the opposite and you're doing that to both of them, it's still adding, right? It's 2, and then 6 plus -4 is 2. It does change how we graph, because we're graphing the opposite, so it's backwards. Let's see. Okay, we got one more thing we gotta talk about. Oh, stop it. I'm gonna give you a shortcut, you whiner butt. Do you want the shortcut or not? We are absolutely recording. Okay, so do you remember if I say to you, What does that represent?
Magnitude.
Magnitude. That represents magnitude. So if I said that I wanted you to do,
It's okay if you stopped the lesson just to give me a lesson
if I asked you to do the magnitude of 4 times v, okay, if I asked you to do the magnitude of 4 times v, the shortcut for this is that you could do 4 times the magnitude of v. So let me show you. So let's say that vector v is 3, 4. We're making this nice. So we're going to do this 2 different ways. We're going to do the shortcut and we're going to do the long way. Okay, so let's find 4v first. So 4v is equal to what? 1216, yep. Okay, that's scalar multiplication. Since I've thrown a lot of things at you today, that is scalar multiplication. Magnitude then is the square root of x of delta x plus delta y. It's been a while since we reviewed that. It was last Thursday. This is one reason that component form is so lovely, because you just take these numbers and that's going to give you the magnitude. Okay, I believe that's the square root of 200. So 144, 256. Square root of 144 is 12 squared. 256 is 16 squared. Add those together, it's 400. No, 200. 400.
I got 20 as mine.
Yeah, because you got to do the square root.
Yeah, I got 20. Where did you get 200 from?
My brain not working. That's where it came from.
You're so mean.
No. This is 4. Your shortcut is 4 times the magnitude of v. So the magnitude of v would be square root of 3 squared plus 4 squared. This is 9 plus 16, which is 25. So 4 times 5, because the square root of 25 is 5. Now, let me show you. You're going to be like, I don't really care. Okay? It didn't save me any time. It will save you time when it's like this. So let's say that you life is rough. Let's say u is 1, 3. And I want you to find the magnitude of u. And then I want you to find the magnitude of 2u. Okay, this is our last example. And this is the one that's going to let you see that you can save yourself time if you use the shortcut.
Miss Douglas.
What?
I think you're captain. I don't think I need to use the shortcut.
Don't use a shortcut then.
Dude, someone didn't include their calculator. There's just like a bunch of the quiz answers on there.
One squared plus 3 squared. So 9. Oh, so 8.
Okay, so what's u? U is the square root of 10. What is 2u, the magnitude of 2u? Correct. So if you didn't do that though, if you just did this, it would be 2 and 6, that's 2u. Okay, 2u is 2 6. So if you were to do this math, it's 2 squared plus 6 squared, which is the square root of 40. Now here's where the time saving comes in. That square root of 40 needs to be simplified. So remember that? Like that's where you go, okay, 40 is divisible by 2. So that's 20, and that's divisible by 2, and that's 10, and that's 2 and 5. And back to down to 1 here. And then you go, oh, that's 2 2s, and then the 2 and the 5 stay on the inside. And you have to get that to be 2 times the square root of 10. Okay, if you do it the shortcut way, then you find u and you pop the 2 in front of it. So it's 2 times the square root of 10. It keeps you from having to simplify those roots. Yeah, it's significantly nicer. So listen, if we're talking about, this is an important piece. So listen, if you're talking about, this is a scalar here. So we're talking about k times u and doing the magnitude of that. If you want to do it with the shortcut, this has to have the absolute value. So if it was a negative scalar, it's going to be an absolute value in there. Because magnitude will always be positive. So this is your shortcut. Everything else, all the other properties of vectors are pretty self-explanatory. So, for your homework.
Are we serious in the last 2 minutes of class?
And we got it doesn't even say we
And I put it in school after.
Yeah, the quotas are allowed. We get 10% of the money they're making. It's a fundraiser.
Javon, you never have time for this. Do this during success.
He's got a happy hour up. You don't got time. Listen, what are you doing at the squirrel?
It's a baseball fundraiser. And we get like 10% of the money.
Oh, so is it about the money?
Yeah, it's not money. It's like helping out or anything. No. Like
I don't know.
your family, more people than more money.
See what time I get done.
Squirrel burger.